Stanford University.
Okay, well, welcome to CS 193P, Developing Applications for iOS. This is fall 2011. I'm Paul Hegarty. I'll be your Master of Ceremonies for this quarter. Today we're going to talk a little bit about what this class is about. Make sure this is the class you're really interested in taking. I'm going to give a really brief overview of iOS. I'm going to assume that most people interested in this class already are familiar with iOS. Maybe they have an iPhone in their pocket or an iPad and they already know what's going on. They just want to be able to develop applications for it. Then I'm going to, at the end, cover two actual lecture topics that you're going to need to know for this quarter. The first is basically the design paradigm we're going to use to build applications. And then I'm going to give you a little peek, a little taste of the language that we're going to use, which is Objective-C, an object-oriented version of C. So yes, you have to learn another language. But for you computers, this is CS 193P. At this level of CS, another language should just be nothing. So we will cover that. And it's not an intent to teach you Objective-C in 20 minutes. It's more just to give you an exposure. All right. So what will I learn in this course? Well, number one thing you're going to learn is how to build cool apps. All right. iOS as a platform, it's really easy to build really powerful applications in a very short amount of time because it has really powerful infrastructure for building applications. The things you build they live in your pocket. You can whip them out, hey, look at what I built. So that's kind of cool as a developer, not to have something that you have to wait for it to show up in stores or people download. You can show it to them right there. If you do come up with an application that you really like, it's really cool, it's really easy to market and distribute it, right? Just throw it on the App Store, bam, money starts pouring in. And lastly, it's a very because of these above things, it's a very vibrant developer community. There's a lot going on in iOS, a lot of startups out there doing cool things from games to personal productivity stuff. And so it's a lot of fun to be working in this environment. And the second thing you're going to learn in this course is real-life object-oriented programming. Okay? So maybe a lot of you have experience with real-life programming. Maybe not. You're mostly students, so perhaps not. You all have to have a good experience with object-oriented programming. And so now we're going to combine those and see, so you can see, hey, with this object-oriented programming stuff that I've learned, what's it look like in the real world? Because we're talking about a real-world, very high-volume environment that people are running applications in. And you're going to see what it looks like to develop in that environment. And as part of that, you're not only going to learn how to just build an app, but you're going to learn a lot of computer science-y things. And you'll all have varying amounts of experience coming in here in terms of the CS classes you've taken. But you're going to learn in this class about databases, networking, all kinds of multimedia programming, multi-threading, animation, all these things listed up here. We're going to do all those things in this class. So it's a pretty action-packed class. And it's a really great class if you want to get a real industry kind of feel for what it means to apply all these technologies. Okay? Prerequisites. So the prerequisite for this class, the most important prerequisite is that you must be a competent, comfortable, object-oriented programmer. Okay? Now, I've put up a bunch of object-oriented terms up here. And all these terms should be very familiar to you, okay? If I start talking about a class or how we're going to add an instance variable or we're going to use a protocol to do something, and you're kind of like, what does that mean? Instance variable? I never heard of that. You're in trouble, okay? Because I'm going to assume knowledge of object-oriented programming, okay? So that's really something to be clear of right up front. If you're not comfortable with these terms, if you're haven't had some experience writing object-oriented programming, it's going to be trouble. And specifically, if you've never written an object-oriented program that uses more than a class or two, like I know a lot of CS 106A, the assignments are write a class that has these 5 methods that does something. That's great. You're just learning object-oriented programming. But by the end of CS 106B and certainly into CS 107, it's going to be more like solve this problem using object-oriented programming, and you have to come up with 4 or 5 classes working together to do it. And that's where we are. Okay? We're at the 4 or 5 to even 10 or more classes working together to build an application. All right? So you don't want to be jumping from 0 to 60 in 10 seconds there, and you want to give yourself, you want to already be at that level where you can put some objects together, understand a little bit about programming interfaces. Okay? Any questions about that? All right, the assignments. In this class, there are 7 weekly assignments. You have 1 week to do them. They are assigned after lecture on Thursday. They are due at the end of the day, the next Wednesday, 11:59 p.m. Pacific Standard Time. They are due, okay? They are individual work only. This is not something where you're going to get together with your friends and say, oh, how are we going to solve this problem? They are not structured as like big projects. They're weekly assignments that are directly having you do what I'm doing in the lectures and in the demos I do in class that week as homework, okay? I teach the same way every week. I'll tell you about it in lecture. I'll show you by writing some code right here in front of you, and then I'm going to ask you to do it in homework. The same thing 3 times. So everything I present in this class, you're going to see 3 times, those 3 times, okay? Over and over every single week. So the homework is individual work for that reason. It's graded on a check plus, or check minus basis. And every homework assignment will have a required task section and an evaluation criteria section, okay? So if you complete all the required tasks as per the evaluation criteria, then you'll get a check. If you do a great job of that, you might even get a check plus. If you don't implement one of the required tasks, or you don't do it in the way the evaluation criteria describes, then you might get a check minus. There is extra credit in every single assignment. I encourage you to bank some extra credit just in case later in the quarter one of the concepts that we introduce is a little hard to understand and maybe you don't do one of the required tasks. Some of that extra credit can flow over and pick you up there. The amount of extra credit varies, and some extra credit things are worth more than others because some of them are really trivial to do, some of them are quite complicated. But all of the extra credit is not just there for extra credit, it all expands upon what you learn in that week, okay? Lateness is the #1 fail factor in this class, okay? If you start getting behind, you're probably done. And that's because these 7 homework assignments all build on each other, okay? Why do I do it that way? 2 reasons. One, if you're building I want you to get to the end of this class and be able to build a significant iOS program. I don't want you to be able to just build toys. I want you to build something real, okay? Well, something real is going to require the amount of code that a few weeks of doing homework assignments will build up to be. So in these 7 assignments, I'm actually only going to have you build 2 applications. One the first 3 weeks, another one the last 4 weeks, okay? Those at the end will be 2 pretty significant applications. Now, the other reason for doing it this way is you have to learn as a real programmer, a real world programmer, to live with your mistakes of the previous week, okay? So you're going to do some things in week 1, you're going to make mistakes, something's not going to work, your TA is going to give you feedback. You're going to have to go back, fix those things, and build on it in week 2. So some people often ask me, hey, can I have the solution, as if there's one solution to any homework, there's not, but can I have a solution for week 1 so I can start on week 2? No, you got to live with your mistakes from week 1 in week 2. All right, so that's why we do the builds. But the problem with the builds is the lateness. If you start getting late on one, now you leave yourself very little time for the next one. That one might start being late and it just starts shifting out, okay? But I do understand that things come up, you get sick, family emergency, whatever. So you get 3 free late days per quarter. I strongly recommend, of course, that you save them for when you're sick or have a family emergency and not just kind of fritter them away on, I don't want to do that today. You know, if you use more than 3 late days, it'll affect your grade. How much? Kind of depends on the degree. You know, if you're only 1 or 2 late days over, it's not going to kill you. If you're a week or 2 weeks late, which has happened in this class, well, A, you're going to be so far behind, you're just never going to get this material. But B, that's going to have a significant effect on your grade as well. Okay? Any questions about that? And then there's a final project. So the first 7 weeks are these 1-week homework assignments, and then the last 3 weeks you'll be working on a final project. Okay? I will accept some teams of 2 here, but I prefer not to. It's quite, first of all, 6 weeks of work is what the scope would have to be. That's a big project, okay? In iOS, you can build a big app in 6 weeks of homework time. So I don't necessarily want to bring such a monster to the table here. Also, it's very difficult if there's 2 of you for me to measure who did what and who learned the stuff and who didn't, because this is a computer science course. The whole point is for you to learn the stuff and us to measure whether you learned it, okay? So 2-person teams makes that difficult. But the right proposal, properly, convincing me, I might allow it. Everyone will have to submit a proposal, whether it's a team of 2 or not, and that proposal will have to get approved. And mostly the thing that goes back and forth, this is not likely to be a here's my proposal, okay, approved. It's going to be back and forth, and most of the back and forth is about me asking you to cover as much ground in iOS as you can. Breadth is more important than depth on this final project. I will say that many times, okay? Part of your final project also is to give a keynote presentation of around 3 minutes, maybe slightly less. And you can think of that as the room is filled with venture capitalists, and you're pitching to them why your final project they should invest in, okay? Or at the very least, the room is filled with customers for your app, and you're trying to explain to them what it does and why they would want to use it, okay? That is a required part of this class. Those 3 minutes will happen during the final exam period of this class. So if you have a conflict with the final exam period, maybe that's a reason to take this in a different quarter than this one, okay? Okay. So that's it on the logistics. Any questions about logistics? Okay, good. Yeah.
When is the final presentation? What day?
Yeah, the question is, when is the final exam scheduled? And I don't know. They have not told me yet. They seem like they tell me halfway through the quarter, this is when it is. I'll certainly, the instant I know, I'll post it on Piazza. But, it's whenever the normal slot for this class would be. So, all right. Now, very brief overview on iOS. What's in iOS? Now, this is going to be super brief because, like I said, most of you probably know what's in iOS. And I got other stuff to cover that's really important. But I'm going to divide iOS into kind of 4 layers. These are fairly arbitrary layers here. And these layers are closeness to the hardware. So the bottom layer is the closest to the hardware, and the top layer is the closest to your programming environment for the end user, okay? So at the bottom layer of software in iOS is basically a mock 4.x BSD Unix kernel, okay? It's the mock OS 10 operating system, basically, targeted for this device, but that gives you a lot of power to have a full multitasking Unix kernel at the base. And it's quite remarkable that that kind of operating system is on a embedded device like this. At that layer, that gives you a lot of fun things like networking and sockets and security at that layer and the file system, obviously, things like that. Most of this API is C API, not object-oriented, okay, because it's the Unix code, basically, and things built on the Unix code, not object-oriented. We won't be programming in this class at that layer very much, if at all. Built on top of that, though, is a layer that starts to be more object-oriented, okay? And it's providing a lot of the same services as the layer below, but with object-oriented API. For example, there's a socket class, right? So that you can do sockets using an object-oriented mechanism. This is also where we have some language runtime support for things like multi-threading, which we're going to do in this class, because a good interactive user interface program needs to use multiple threads, because you've got to keep that main thread that's interacting with the user, keep it free to be interacting with the user all the time. You're also going to have the collection classes here, like arrays and dictionaries, and all that kind of mechanism is all in this layer. So you can think of this as kind of a mostly object-oriented layer that's providing basic functionality and then covering that core OS. Now this next layer, the media layer, it is kind of the next layer up away from the hardware. However, it's a little bit of an orthogonal layer because you have to remember that the iPhone, the iPad, the iPod Touch, these are fundamentally multimedia devices. Whether it's audio or video or a combination, you got FaceTime going, you got your iPod library with all your music for the last 20 years in there, it's a multimedia device. So multimedia code runs throughout iOS. It's just everywhere. It's all built in, okay? And so almost any API that you see from the core services layer on up is going to be thinking in its mind, in the designer's mind, about multimedia. What kind of media do I need here? How does this plug in? Et cetera. So there's going to be a lot of multimedia going on in this class because this device is fundamentally really good for that. Okay? And then finally, we have the top layer, which is the Cocoa Touch layer. Okay? Cocoa is the name of the application development environment for Mac OS X. On iOS, we call it Cocoa Touch. All right? And this is really where we're going to spend 90% of the time in this class, is learning this layer. And so this is where all your buttons and sliders are, all your views, all the navigation mechanism for navigating through a user interface, things like alerts. This is where high-level media picking, like the camera, where someone wants to take a picture or something from their photo library. That's all happening at this Cocoa Touch level. This is entirely object-oriented at this layer, and not just object-oriented in terms of you call methods to access the stuff instead of objects, but object-oriented in terms of it has a design paradigm that you have to understand, which I'm going to explain here in a moment, that you plug into, that makes it really easy. Very few lines of code to write as long as you're swimming downstream with this design paradigm, okay? So that's iOS in a very small nutshell. The two things let me do one quick thing before we dive into some actual learning here, which is let me talk about the platform of the development environment. So the last few slides were iOS itself, what's in there. This is when I'm a developer and I sit down to develop, what am I going to see? Okay, well, you're going to see some tools, primarily one tool, Xcode 4, okay? Almost everything you do is in Xcode 4, okay? Apple has definitely taken the approach of one application that does it all. And they've been making it do more and more so that it's even closer to all. There is this Instruments, which is almost like a plug-in, kind of attachment to Xcode that lets you measure what your application is doing, its memory usage, its performance, its graphics performance, things like that. And so we'll talk a little bit about Instruments. But most of what we're going to do, we're going to be sitting in Xcode 4. Okay? Also, as a programmer developing, you're going to see a new language. Okay? Objective-C. We'll see a lot more about that today. There are a lot of frameworks. You're probably used to terms like package in Java or libraries in other languages. In iOS 5 environment, we call them frameworks. And the frameworks just are collections of objects that work together to do a certain thing. So there's the foundation framework, which is where array and dictionary and all that is. There's the UI kit, which is where sliders and buttons and views is. Core data, object-oriented database access. Map kit, a bunch of objects for doing Google Maps. Core motion, a bunch of objects for measuring the motion of the device, gyro and accelerometer and all that stuff. So we're going to learn a lot of different frameworks. And finally, you can't really describe the development platform without including this design strategy, which is MVC, Model View Controller. So how many people in this class have designed something using a Model View Controller paradigm? Okay, so about half, and that's pretty typical. And so I'm going to spend the next 15 minutes or so describing Model View Controller, how it works. And then on Thursday, all I'm going to do on Thursday is build an application. And that application will very clearly show you how Model View Controller works in the Xcode iOS 5 environment. So let's talk about Model View Controller. What is Model View Controller? The main idea of Model View Controller is we're going to take all the objects in our program and we're going to put them into one of three camps. Okay? We're going to put them in the model camp, the controller camp, or the view camp. Model View Controller, that's why we call it that, okay? Model, controller, or view. Now, what are these three camps? Your model camp is what your application does. So, for example, if you're building a space shoot-'em-up game, then this is where the spaceships are in outer space what planets are, where they are, how many guns each ship has, how much damage it can take. Those are all part of what that program is. It's a space, it represents spaceships in outer space. That's its model. Now notice I didn't say anything about where the ships are on the screen. Okay? The ship on the screen has nothing to do with the model of the program. That's where the controller and the view come in. So the controller you can think of as the objects that control how your model is presented on the screen to the end user. Okay, so it's kind of the glue. It's the thing that takes the spaceship's position in outer space and figures out, okay, how am I going to show this on screen? All right? Or how many guns the spaceship has, how am I going to show that on screen? Where does that appear? Is that dots in the corner? What's something drawn on the device, etc. So that's what the controller is. The controller controls how your model is presented in the UI. And then the view is your controller's minions. Okay? The view is just objects that your controller uses to do what it does, okay, to get this thing on screen. Now, we try to make objects in the view camp be as generic as possible. Okay, generic is about like buttons and sliders that come from Apple, for example. Know absolutely nothing about what kind of application they're going to appear in. All right? It's up to the controller to take these generic view minions and use them to do what the model needs to do, do what needs to be done to display that model on screen, okay? So really the view wants to be generic objects. That's an important thing to think about. Because a lot of programming systems, people have the views have a lot of application-specific knowledge in them, right? And it's all about how the views decide to draw them. And we want to move towards reusability and also understandability by making our views generic, okay? So once you have these three camps, then it's all about managing the communication between the camps. So now I'm going to talk about what communication is allowed and how we achieve that communication. So let's talk about controllers talking to their model. Okay, so this is a controller object wants to send a message to an object in the model, and that is 100% allowed. Green arrow going that direction. The controller can say anything it wants, ask any question of the model. The controller knows everything about the model. Okay? Because it is the controller's job to get that model on screen somehow. So it needs to be able to have full access to the model. Now this arrow only goes one way. This green arrow is pointing from the controller to the model. So this is the controller knowing about the model. Okay? So that's fully green, no problem. You notice I've drawn what kind of look like road markers there. Okay? And you can see that on the side from controller to model, it's dashed white line. That means, sure, cross over this line anytime you want. Okay? And these other lines you'll see are not always dashed. What about the controller talking to his minions in the view? Also green arrow. Okay? The controller is responsible for getting the model on screen. It's got to have full ability to do anything it wants with those views. Okay? Set them up, tell them to do things, arrange them on screen, communicate data to them, etc. So that arrow is also green. So that side of the road is also dashed white line. Now, you see the word up there, outlet. Outlet is a term we use to describe a property in the controller that it uses to talk to its views. So we will create outlets from our controller objects to our views, and those outlets will be properties through which the controller will talk to its views. Okay? So I'm just introducing this phrase outlet right now. How about the model and the view? All right, for the purposes of this class, they never talk to each other ever. Now, I'm sure you can understand why the model would never talk to a view. Okay, the model is user interface independent. Right? You could have a model for a space shoot 'em up game where the user interface is command line. Move ship to XYZ, shoot ship. I mean, you could. It would be kind of silly, but you could. So the model is completely UI dependent. So I think you all agree there should be no communication from the model to the view. The model should have no idea what the views are. And the other way, some people say, well, I want to build a custom view that knows all about my model so I can display it. And while that sounds attractive, the reason that that's not necessarily such a good idea is reuse, because when you write that custom thing tied to that model, whenever that model changes, you're going to have to rewrite that custom thing. Those things are linked, okay, in a way that makes it so that the view can't be reused. And also the model can't be reused with a different UI. So, iPad comes out and it's got more screen real estate and you want to do a different UI for something. You got to rewrite a whole new view. Better to put that code in the controller, okay, and try to build a more generic view object. The other reason is that the model will, if you have a view object that's talking to the model, now you've got everybody talking to the model. The views are talking to the model, the controller's talking to the model. So the model now is a little bit like under siege, okay? And when you're trying to figure out what's going on inside my application, it's a lot easier if you know that only your controllers are talking to your model, okay? So you keep the views out of it. The views are just minions of the controller. Let the controller do the work there. So we are, in this class, never going to have the view and model speak to each other, ever. Double red line. I'll give you a ticket if you cross over there, okay? So don't do that. How about the view speaking to its controller? Is that allowed? Can the view talk to the controller? And the answer there is sort of. Okay, that's why it's yellow. That was yellow. The communication between the view, which is a generic object, and the controller, which is very specific to how this application presents the model on the screen, is got to be blind, meaning the view can't know what class of object it's talking to, and it also has to be well structured, so that in Xcode 4 we can connect up the view to the controllers in a structured way, right? So that we understand how to do it. So here are the ways that a view can talk to a controller, okay? Structured ways. One is called target action. Okay, target action, very simple. The controller just hangs a target basically on itself, and then it hands out an action to its view. Okay, some object in its view, and then the view, when something happens, like a button gets touched or a slider gets moved, it sends that action up to the target, and so the controller's like, oh, the button got touched. Now I'll go do something. All right, so this is a mechanism whereby the view is talking back to the controller, telling it what's going on, but view doesn't really know much about the controller. All it knows is to send this target action. Very simple, structured communication there. But there's more complicated communication that needs to happen between the view and the controller. For example, you got to sometimes keep the view in sync with the controller and vice versa. So a lot of times views have a situation where they want to tell the controller something happened. Okay, that's the did up there. Or something's going to happen. That's the will. Or they want to ask the controller, should I allow this? Okay, so those kind of will, did, should kind of questions, the view needs to be able to ask. All right? And the way it does that is that the controller sets itself as a delegate using protocols. You should probably all hopefully know what object-oriented protocols are. And we're going to talk about how to do that in Objective-C. They're going to set a protocol so that when these will and did and should things are going on, the controller gets to be involved. All right? But again, the view doesn't have to know what class the controller is, just that it responds to these will, did, and should delegate methods. Okay? So delegation, that's called delegation. That's another way that we communicate views to controller. Another important thing is that views do not own the data that they display. That is very important to get this in your head. That's why it's flashing red. You need to understand views do not want to own their data. Okay, let's say that the view is a table, okay, a table of information. It just shows a bunch of rows of information. Okay, that's the view. That view does not want to have an instance variable or any kind of storage in it that points to the things in the table. Like the 10,000 items in your iPod library. Those 10,000 items in your iPod library don't want to be an instance variable in this view that displays a table. Okay? That kind of design makes it so that, for example, that view has to know how to do database management and get updates when the iPod library changes. Those aren't nothing to do with being a view. Those are things a controller or even the model wants to do some of those things. Okay? So if the view doesn't own the data that it's going to display, how does it get it? Well, in a similar way to delegation, okay? It has some protocol, like this one here is saying data at and count, so this would be good for a table, right? Where it can ask somebody, how many things are in the table? Okay, 5,000. And then it says, okay, I want the data from line 100 to 150. Give me those, and I'll display that. Okay, so it's basically asking for its data as it needs it. So that could be very high performance if the other end of that knows how to manage a huge database and only extract the pieces that you need, right? Because if you had a table of 10,000 songs in your iPod, there's only 7 of them on screen at a time. So you want to be able to have that performance, and you don't want that performance code to be in a view, right? A view is just a generic thing, displays a table of objects, and it's up to the controller and the model to work together to provide that information efficiently. So same kind of thing here. The view gets a data source set in it, okay? And the data source has these methods, and the controller responds to them. Notice that the data source and the delegate are always the controller, right? Now, they could be a third object designated by the controller, but they would never be the model, okay? The controller has a job, which is to interpret and format the model information for the view. Okay, so it's the one that wants to respond to all these delegated things because it's getting the model's data and figuring out how to display it on screen. That's what it does. So it wants to have an opportunity to be involved in that loop. Now, you might have a lot of these data at and count methods. They might be one-liners. Just one, they just ask the model, what's the data at that, and the model just gives it to it. But that's okay. Even if it's one line, it's still an opportunity for the controller to be involved in there because that's its job, to take the model and display it on screen, right? I keep saying, I've said that about 5 times, that's the controller's job. Controller is very important in iOS development, okay? And you have to give it a chance to do its job. So we never go straight across and have the data source be the model. All right, one more thing here. Can the model talk to the controller? Now, this one should be obvious. Absolutely not. Okay, the model is user interface independent. It knows nothing about its view or its control, its user interface rather, and so it couldn't possibly talk to the controller. Okay, because the controller, its job is user interface. That's what it does. It uses the views to present the model on screen. So, but what about the times that something changes in the model, and you want to update the controller? Okay, so you have a database and somebody else writes to the database. Okay, you got the spaceship game and some other client, it's a networked thing, and some other client shoots your spaceship. Now the model has changed because your spaceship took damage. And the way we do that in iOS is using a radio station-like information broadcast mechanism. There's 2 of them actually, notification and key value observing. All right? And what happens here is the model, when things change, it broadcasts on a radio station that the controller is tuned into, and the controller hears, oh, something changed. I better go ask the model about this. Okay? So it's all completely blind, right? And it's all somewhat asynchronous. It's all happening in the main thread of the application, but it's mostly asynchronous. And so that mechanism happens. Now, this KVO and notification, it can also happen between view and controller. It would never happen between the view and the model. Okay? The view would never sign up for a radio station that the model broadcasts. But the view might sign up for something in controller, and the controller might also sign up for something in certain views. So the radio station model is really nice because it's blind, but it's somewhat limited too, because you can really just get notified that something happened. You still have to go then talk to someone you're allowed to talk to make something happen. So now that we have all these mechanisms for getting these different camps to speak to each other in a structured way, we need to build complicated applications, because complicated applications have a lot more than just one controller controlling a view. They might have, 100 controllers, or certainly a dozen controllers controlling lots of different views, right? You have a view that's got a login screen, and when you log in, it shows you all your personal information. Then you click on something, it shows you a table of information. You click on something in that table, it shows you something else, etc. That's a lot of, piece of information being viewed and managed from the controller. So how do we build those complicated applications? And the answer is that we combine MVC groups into big graph of MVCs. Okay? And you can see in this graph that some of the controllers, which are in purple, their view, their minion, is another MVC. Like, do you see the one up in the middle, in the center, right? Look, it's one of it actually has 3 MVCs being its view minions. You see, how it's doing that, coming across that view line. So it's very common that you have something in a view, you click a button, and it gets another MVC to put some screen on, some page of information up on the screen and get some other information for the user. All right? But the good thing about this graph is that all the arrows are coming across predictable boundaries. So this program, you can look at any one part of it and you know what's going on in that one part. As opposed to a graph like this, where everybody's talking to everybody, this is bad, okay? This is ununderstandable. We can't track what's going on. If we have a bug, we got to figure out who's talking to who might be sending this message to me, under what circumstances. It's basically impossible, okay? So we're not going to build applications like this. All right, question?
Every view in every model has only one controller.
Correct.
And controllers talk to each other as views?
Usually a controller would only have a pointer to another controller as its view. Yeah, it would be asking that controller to essentially display something for it. Because controllers, their job, they know how to take information and display it on screen in a complicated way, and they use the views as their minions. So a controller could be displaying something so complicated they need another controller to go do it, like a whole nother screen of information, right? So anyway, so that's that. Okay, so we have about 7 minutes left, which should be enough time for me to give you a quick overview of Objective-C. This is a contrived example. I'm going to keep with the spaceship theme. We're going to have a little spaceship class here. I'm going to show you what a spaceship class would look like in Objective-C. The main thing I'm going to show you today is something that's a little different in Objective-C than in other languages, which is how we store information, store and retrieve information in an Objective-C object using properties as opposed to using instance variables, which is probably what you're used to. And we still have instance variables. They're kind of second-class citizens in Objective-C. The properties are the first-class citizens. And don't freak out here. This is just your first glimpse of Objective-C. I don't expect you to come out of here and be like ready to program in Objective-C. It's just that on Thursday, when I go over our sample program, I don't want you to be like, oh, what is that? I've never seen that before. I can't figure out even what he's saying. So this is just a little bit to soak in and get ready. And actually, I guess we have a little more time than that. All right, Objective-C. So Objective-C is a strict superset of C. Okay, so it is C. So just like C, in C you have .c files, where your C code is, and you have .h files, which is your header files that tell people what they can call inside your .c file. Well, Objective-C is the exact same way. It has header files, and it has implementation files. But the implementation files in Objective-C are .m, okay, as opposed to .c. All right, so an Objective-C implementation file, historically, .m. All right, just kind of so we know that this is Objective-C. Yeah.
Since it's a strict superset of C, will it still compile if you have .c files in there?
Yeah, absolutely. The question is, if I have .c files in my program, will they compile? Absolutely. In fact, you can even have C++. But we're not going to cover that in this class, but you can have C++. The compiler knows how to compile C++ as well. You can include that. None of the iOS API is C++ based, so that would be some library or something separate that you'd be doing. But anyway, so you have a .h and a .m. Here's what kind of the skeletal bare bones of the .h and the .m look like. So both of them, notice, have an import at the beginning. So import is, for some of you who have not seen this in other languages, import's kind of like include, #include in C. It's just smarter than include, so if things are getting included more than once, and it also deals with pre-compiling header information, stuff like that. So it's just like basically include. The header file is including the header file of our superclass. Okay? So the implementation file is including the header file of ourselves, spaceship.h. Okay? So let's look on the left now. This is our header file. And you can see this @interface keyword. That basically says I'm declaring a class. This is the interface for this class. And spaceship is the name of this class. So we're creating a class called spaceship. And then the colon and vehicle is the superclass. Okay? So a spaceship is a vehicle, right? So it's normal inheritance. And then you can see down the lower left, it says @end, right? So everything our interface for our spaceship is going to be between that @ interface and the @ end. And similarly, on the implementation side in the .m, it starts with @ implementation, name of class, no superclass specified here. Okay, we've already specified it in the header file, and we're including our header file in our implementation, so we don't need to say it again. And then @ end at the end. So everything, all our implementation of all of our methods go between this @ implementation and the @ end. Okay? One thing that's important to understand about Objective-C, private versus public is all about implementation file versus header file. There's no private keyword, public keyword like you might be used to in Java or other languages. Okay? If it's in the header file, it's public, and if it's not in the header file, it's private. Everyone got that? That's an important thing to recognize. So you might ask, what if I want to declare some methods in my implementation file that are private? And so yes, you can also have an @ interface in your implementation file. Okay, it has a little different syntax there. It doesn't, again, does not specify the superclass. Instead, it has this open parentheses, close parentheses. Okay, we'll explain why it has that next week when we talk more about the language. But so inside this little interface, @ interface, @ end, and you can only have one of these at the top of your implementation. You can put other method declarations. For example, if you need, let's say you had recursion, and you have method A that's going to call method B, and then method B is going to call back to method A. Well, this is C, so you have to declare the thing before you call it. So you could put method B in this @ interface at the beginning so that you can call them, right? Because it has to be declared before it's called. So basically, @ interface with the parentheses allows you to have a private interface. Everyone cool with that? All right, so now we're all ready to add some methods to our object here. So I'm going to add a public method. Okay, and I'm only adding this method just as a way to show you the syntax, okay? So this method is called orbit planet at altitude. Okay, that's what we would say this method is called. It has 2 arguments, and it returns no value. So the void that you see on the left there, that means this method returns no value. Okay? Now, that void could be double, in which case it would be return a double precision floating point number, just like this normal C double. It could also be a pointer to an object, okay? Just like the first argument is. You see that first argument, a planet? That's the name of that first argument. Its type is planet star, which means a pointer to a planet object, an instance of a planet, okay? Notice that I've had to import the header file for planet in my header file as well, because I can't use that symbol, planet, which is the name of a class, unless I've imported it. Also notice that the arguments, the a planet and the km there, and those, by the way, the word a planet and the word km could be anything you want. Think of them as part of the documentation, because this is a public method, and so I've made the km be km because I want to let people looking at this method know that the altitude, I expect it in kilometers. Okay, so I put km there. It could be, I could put any keyword I wanted there. But this has 2 arguments. One is a pointer to a planet. The second is a double. Notice how the, and this is on 2 lines, but this could all be on 1 line. It wouldn't have fit on 1 line here. And I've lined up the colons to make it look nice, but it could all be on 1 line. Notice how the arguments are interspersed in the name of the method. Okay? So in Java, this might be orbit planet at altitude, open parentheses, a planet, comma, km, close parentheses, right? Which, this is one of the great things about Objective-C. It makes it very readable because all of the arguments are interspersed with the keyword that describes what you want. So the caller of this is going to say, Mr. Spaceship, please orbit planet, this planet, at this altitude, 200 kilometers. Okay? So it's much more readable than having 4 or 5 arguments and having to see which ones match up with which out in the parentheses off at the end. Okay? So that's a great, really nice thing about Objective-C, but it takes a little bit of getting used to. Now, every argument has to have a keyword and a colon before it. So like orbit planet colon, an argument, at altitude colon, an argument, something else colon, an argument. Okay? The keyword should describe what the argument is. So in this case, it's a planet, and we're saying what we're doing with it. And the second one is an altitude, right? So you want to be very descriptive in the names of your methods. Okay, question?
So is it common to end up with pretty long method names?
Very good question. So the question is this going to result with very long method names? And the answer is absolutely. Okay, you're going to have very long method names and very long variable names in iOS when you're programming, if you're doing a good job. And that's okay, though, because Xcode does escape completion essentially to the max. It is constantly trying to help finish up the method that you're typing or the variable name. You'll see that on Thursday. So definitely you want long variable names, definitely long method names, very descriptive. You want your code to read as close to reading just the English language as you can, and you'll see how that works as time goes on. Okay, so that's a method. That's what a method declaration looks like. Okay, we're declaring the method here, and we're making it public. If we didn't want it to be public, we could have put it in the @sign interface on the right, but we put it in the @sign interface on the left, so this is public. Other classes can call this. Here's what the implementation of a method looks like. So it's the same method. Notice I've put it all on one line here just to show you what that looks like. And it's exactly the same, except for there's no semicolon at the end, right? You could put a semicolon there. I think the compiler will tolerate that, but you really shouldn't have one there. And then you just have open curly brace, close curly brace, and you put your implementation in there. Okay? Simple as that. And we'll go look at a sample implementation of Orbit Planet just so that we can see what calling methods look like and stuff. So here I've added a couple more methods here. Set top speed, which takes a double. I want it as a % of the speed of light, so I've called the little keyword there, % speed of light. It returns void. I'm setting the top speed of my spaceship here. And then double top speed is a method that takes no arguments, that just returns a double, which is our top speed. Okay? Now, having a pair of methods like this where you're setting something and then getting it is super duper common. Okay, very, very, very common. In fact, so common that there's extra syntax in Objective-C to support this, which is, and actually, before I even talk about that though, so set top speed and top speed would have implementations. I'm not going to talk about what those are. That's why I put those question marks there. But this it would look like, as you would expect, right? Okay, matches the header file there. So anyway, so the special syntax that we use for things that we set and get like that is called a property. All right? And what we do, if we want a public property, is we put this line in our header file, @sign property, parentheses, some keywords, get to that in a second, type, the type of the property, in this case a double, and then the name of the property, top speed. Okay? So saying @sign property, non-atomic, double, top speed is exactly like saying those two lines at the bottom, set top speed and get top speed. In other words, @sign property declares a setter and a getter for that property. All right? And the property's getter is always the name of the property, just like top speed is the getter right there, the get, see it? And the setter is always the word set, capitalized name of the property. Set, capitalized name of the property, and then a colon, and then the type. So that's why @sign property, non-atomic, double, top speed would create those two methods. Now, that non-atomic, don't worry about that. We always are going to put that in this class. All that means is the setter and getter is not thread safe. Okay? And for those of you who know about threads, you'll understand when you're setting something, you want to make sure that some other thread is not smashing on the data structure that's setting something at the same time. If you don't understand multi-threaded, don't worry about it. We're going to be talking about it later in the quarter. That we're always going to make our things non-atomic. The reason for that is all of our UI happens in the main thread anyway. We put other things in other threads, but the UI we're going to put in the main thread. Question?
Just to clarify, you can still keep your getter and setter lines down below, or no? Or
Great question, and the answer is no. So here I've taken away the set top speed and the top speed because I don't need them. When I do that @sign property, non-atomic, double top speed, it essentially declares the setter and the getter. I could still call them like setters and getters. They're there. It's just that I don't have to declare them twice. Question?
You don't specify a property as non-atomic. Is it by default like thread safe or atomic?
Yeah, the question is if I don't say non-atomic there, is the property going to be thread safe? And the answer is yes, which means locking code will be generated for you, you know what I mean? Or you have to do locking code yourself if you're going to implement the setter and getter yourself. So that's, for now, why we're always going to do non-atomic. So anyway, so we would never declare the @sign property and then also declare the setter and the getter. That'd be redundant, okay? Because it's exactly the same thing. So how about the implementation of the setter and the getter? This set top speed and top speed that I had before on the right, I didn't tell you what the implementation was, but whatever it was, that would have been fine, okay? As long as those two methods are implemented, the property is properly implemented, okay? Because all the property is really is those two methods. That's all a property is. And so the thing that's different about Objective-C is that we don't access our instance variables by going straight to the instance variables. We always go through setters and getters for our properties. And you might say, well, that sounds pretty inefficient, calling a method every time I like it. The overhead of calling a method compared to the overhead of drawing on the screen is infinitesimal, okay? Now, if you were building some kind of complicated algorithm that you were calling something thousands of times in a tight loop, okay, maybe then you're going to want to go direct to the instance variable. But if you're responding to a user touch on the screen, that takes, you know, many, many milliseconds for that finger to go down and come back up, and you know, calling overhead of a method 0, especially since Objective-C method dispatching, super fast. I mean, optimized to the very instruction, okay? But just like we have @sign property to declare these properties for us, we have another magic thing, @sign synthesize, which will implement the properties for us, okay? So that we don't have to do this implementation down there. So what does @sign synthesize look like? Very simple. @sign synthesize, the name of the property, and then equal sign, and then some variable name, basically, that it's going to use in its implementation as the instance variable. Because it's a setter and a getter, and so @sign synthesize, all it does is let you set and get it. It doesn't do anything else. So it needs to use an instance variable, and so we do that equal sign to specify the name of the instance variable. And we usually use, well, first of all, you want to be consistent with what name you use, and underbar and the name of the property is very common, okay? That's a very common naming convention. Some people say ivar underbar, name of the property, something like that. That'd be fine too. I don't really mind what you use there as a naming convention, but just be consistent so that all your properties get synthesized with an instance variable behind the scenes that has a well-defined name. If we didn't say equals underbar top speed, it would still synthesize an instance variable to use, because it's got to have one, but it would use an instance variable with the same name as the property, and that is bad. That leads to bugs in your code, and I'm going to show you, hopefully if we have time on Thursday, exactly what kind of bug that can lead to. So we're, in this class, always going to say equals something besides the name of the property. Underbar, ivar underbar, something, name of the property, okay? Everybody understand that? All right, so what else? Let's look at what @sign synthesize would generate. Okay, what implementation would @sign generate? @sign synthesize generate, and this is what it would do. I mean, couldn't be more simple, right? It just has this instance variable behind the scenes that it creates, underbar top speed. When you call the setter, it sets it. When you call the getter, it gives it back to you, okay? Now, you might say, well, why even have @sign synthesize? Well, because you got a lot of setters and getters, you want to have all this extra little one-liner code all over the place, so it's nice to have it in @sign synthesize. There's also a reason, if you're not doing non-atomic, then this will do the locking for you. That's nice, right? Synthesize will generate much more complicated stuff to do the locking, so that's a nice feature of it as well. But what if we wanted to do something in our setter or getter? Okay, like let's say our spaceship can't go faster than the speed of light, okay, let's say. And so let's say in the setter, we don't want to let you set the speed to be faster than the speed of light, all right? So that's no problem. Okay, first of all, we could just get rid of our setter and getter. @sign synthesize creates them, just like @sign property created the declarations. We could just get rid of them. But what if we did want one? So here I've implemented my setter to make sure the speed is greater than 0 and less than the speed of light, okay? And so I just say if the speed is less than 1 and the speed is greater than 0, then I'll set the top speed. And notice I'm accessing the instance variable here, which is okay. I know the name of it because I've set it in the equals thing up there. Otherwise, if it's not in that range, I just do nothing. So the setter does nothing, right? So if you implement your own setter like this, synthesize will not generate the setter. In other words, synthesize only generates the setter and getter that you don't implement. And in fact, yes, you could do @synthesize and then implement both your own setter and your own getter. And you might say, well, why would I ever do that? Well, because you want @synthesize to create that instance variable for you, underbar top speed, right? And then you go do something with it in the setter and getter. That's perfectly legal as well. Okay? Everyone understand properties and synthesize? Okay, so here's another property. This property is a pointer to an object. Okay, I got a nearest wormhole here. Okay, so wormhole is a class. And notice that next to the non-atomic, there's another thing there, okay, which is strong. So one thing about objects, pointers to objects, we have to manage their memory, right? Because that wormhole is going to use up some memory. And so at some point, someone's going to set this pointer to point to a wormhole. And when we're done using that wormhole, we want that memory cleaned up. So there's two words that can be there. And one of them has to be there if the property is a pointer to an object. One is strong and the other one is weak. Strong means keep the memory that this property pointer points to around until I'm done with it. So it's strong, I'm holding onto this wormhole strongly. Weak means if no one else is interested in this wormhole, I'm not interested either. And just set this pointer to 0, to nil. Okay? Now, this brings up a question, what is the value of a property when the object is first created? And the answer is all properties have a value of 0 when they're created. Okay? So that speed is 0. When we're created, our speed is 0. Now that's probably bad. We don't want a speed of 0. So we might override our getter to say, if our speed is 0, return something else that's non-zero. Or maybe we'll change our setter to allow a speed of 0. And then maybe it's like a space station instead of a spaceship because it can't move. But they're all 0. And for a pointer, being 0 means I don't point to any object right now. Now, one thing that's very different about Objective-C is that if you send a message to nil, what do you think happens? Nothing, right. Okay? A lot of people think, oh, it'll crash, dereferencing nil, 0. No. In Objective-C, it's very important to understand that when you send a message to nil, to a pointer whose value is 0, it does nothing. And in fact, if that message returns something, it'll return 0. It'll do nothing and return 0. Okay? And we rely on this, and we program in iOS knowing this and using it to our effect. Now, this is going to be definitely an adjustment for some of you who are used to putting all kinds of protection against nil dereference and all that stuff. And here, you're going to flip it around and use it to your advantage. Okay? And you'll see that as we go along. So I can synthesize this guy as well. Here I'm synthesizing the same kind of thing. I'm not going to do anything with the setter and the getter, so it creates it for me. One thing to notice, @size synthesizing this thing does not create a wormhole. Okay? It only makes space for a pointer to a wormhole. Someone still has to call my setter, set nearest wormhole, to set the wormhole to something. Does that make sense? It's really important to understand. Every time I teach this course, I always have a few people who say, well, I @size synthesized that wormhole. Why isn't it getting created? That just creates the pointer. You have to call set nearest wormhole to initialize that thing. All right, so we're running out of time. Let's get down here and start doing some code in Orbit Planet. The main thing I wanted to show you here is what it looks like to call a method. Okay, we've seen a lot of declaration and definition of methods. What about if I want to call one? And that's done using this square bracket notation. So here on that first line, double speed equals self top speed, I'm calling my top speed getter on myself. Okay, the way you send a message, open square bracket, a pointer to the object you want to send the message to. All objects in Objective-C are in the heap. We always access them by pointers, always. Okay, always, always. So self is a pointer to myself. Convenient, just like in other languages, this and things like that, self. And then you just put the method that you want. If it has arguments, you just intersperse the arguments with the keywords in the name of the method, and we'll see that in a second. So this, and then if it returns a value, you just say equals the value. So double speed equals self top speed, exactly as you would expect, right? Top speed. To remind you what top speed looks like, it looks kind of like that. We don't have it there because we have our @sign property. And then here's another message send. In fact, here I'm doing a message send inside a message send. So I'm calling my nearest wormhole getter to get my nearest wormhole in square brackets. You see that in the inside there? And then I'm using the result of that, which is a wormhole, pointer to a wormhole, and I'm sending it a message, which is travel to planet at speed. And you can see that the arguments, the planet I want to orbit eventually, and the speed at which I want to travel, are just arguments interspersed along. Now, this method is not done. I'm only getting to the planet here. I've got to enter orbit and all these other things. But mostly I wanted to show you the square bracket notation. That's how we send messages. And one last piece of syntax here, which is that properties are so important that they have their own syntax. So self, angle bracket self top speed is exactly the same as saying self dot top speed. Okay? And the dot notation can work on both sides of an equal. So this one, self dot nearest wormhole, also would work. And if self dot nearest wormhole is on the left side of an equals, it's calling the setter. And if it's on the right side of an equals, you're calling the getter. But it looks exactly the same. Self dot top speed, self dot nearest wormhole. Make sense? You'll see a lot of this on Thursday. A question, yeah.
So just on the nearest wormhole, so self dot nearest wormhole is a pointer. So when you that's true. So when you declare travel to planet, it should return return a pointer or no? What are we doing?
Well, this method, travel to planet at speed, doesn't return anything. But the self.nearest wormhole, the result of that is what we're sending the message to. Right? And self.nearest wormhole is a property which is a pointer to an object, so that's okay. We can send messages to pointers to objects. That's the only thing we can send messages to, pointers to objects. Okay? All right, so that's it for Objective-C. Let me just give you a quick overview of what's coming up here. In the next lecture, I'm just going to do a big old demo the entire time, 1 hour and 15 minutes of pure demo. Okay, Xcode 4, Objective-C, MVC, you're going to see it all. Friday, we have the debugging thing. I already talked about that briefly. And then next week, we're going to learn Objective-C in depth. And you're going to learn about arrays and dictionaries, dynamic typing versus static typing, protocols, categories, all kinds of Objective-C fun. And then the week after that, we'll start doing custom views and all that stuff. All right? If you have any questions, I'll be here. Thanks for coming.
For more, please visit us at stanford.edu.